Why golf balls are dimpled? Which ball would travel faster and for a longer distance in air? Smooth ball or dimpled ball? Spoiler alert, it's all about aerodynamics. To answer this question, we must learn about some important concepts in aerodynamics. We will start our discussion with the concept of boundary layer. So what is the boundary layer? The boundary layer is the layer adjacent to the surface of an object traveling through a fluid where the effects of viscosity is dominant. The figure on the right shows the very thin boundary layer close to the surface of the object using flow visualization techniques. So what causes friction anyways? Before the introduction of the concept of boundary layer, scientists had trouble understanding the source of aerodynamic forces such as lift and drag. This was true until Ludwig Prandtl introduced the concept of the boundary layer in his paper in 1904. By studying the boundary layer and the flow pattern inside it, we can calculate drag forces and gain great insights about ways in which drag can be minimized. The importance of boundary layer. In Sir Ludwig Prandtl's words, a very satisfactory explanation of the physical process in the boundary layer between a fluid and a solid body could be obtained by the hypothesis of an adhesion of the fluid to the wall. That is, by the hypothesis of zero relative velocity between fluid and wall. If the viscosity was very small and the fluid path along the wall was not too long, the fluid velocity ought to resume its normal value at a very short distance from the wall. In the thin transition layer, however, the sharp changes of velocity, even with small coefficient of friction, produce marked results. In the next few slides, we're going to explore these marked results. The boundary layer properties. When the fluid moves past the object, the fluid velocity immediately at the surface of the object are stuck to the surface, and the fluid velocity is zero. This is known as the no-slip condition. As we move away from the surface of the object in the y direction, the fluid velocity increases till reaching the free stream velocity v infinity. The variation of the velocity of the fluid creates a velocity gradient which together with the viscosity creates shear stress at the wall of the object. The shear stress is the tugging force per unit area in the direction of the flow. Hence, by integrating or summing up the shear stress over the entire area of the body, we can calculate the skin friction drag. As the fluid flows past the surface, static pressure and dynamic pressure, which is proportional to the velocity squared, vary at each point as predicted by Bernoulli's equation. If the static pressure increases in the flow direction due to the nature of the flow, the fluid particle motion is retarded even more. This phenomena is known as the adverse pressure gradient. As the fluid particle moves across the surface, it pushes against the shear stress and the adverse pressure gradient. In many situations, the fluid particles run out of steam, come to stop and reverse its direction and start moving back upstream, as shown in the figure. When the flow separates, the pressure in the separated region, the wake region, drops and creates a suction effect. Hence, flow separation is the source of pressure drag in viscous flow. Boundary layer types. There are two types of boundary layers, turbulent boundary layer and laminar boundary layer. The laminar boundary layer is characterized by smooth, regular streamlines as shown in the figure. Turbulent boundary layer is characterized by irregular, agitated motion of the fluid particles. Skin friction drag and pressure drag is related to this type of the boundary layer. In turbulent flow, due to the agitated motion of the fluid element, the higher energy fluid elements from the outer region of the flow are pumped close to the surface. This results in a higher average flow velocity near the surface of the object and different velocity gradient than in the case of laminar boundary layer. We can thus conclude that velocity gradients for turbulent flow near the surface is higher than that for laminar flow, and hence skin friction drag is higher. However, since the fluid element's average velocity is higher in turbulent flow, the fluid elements have more energy to push against the shear stress and the adverse pressure gradient. This delays flow separation, or in some cases, prevents it, and hence reduces or eliminates pressure drag. The drag force for any body is the sum of the skin friction drag and the pressure drag. Since flow separation occurs later in turbulent flow as discussed previously, pressure drag is smaller for turbulent flow. In general, laminar flow is better for slender bodies like airfoils since friction drag is much greater than pressure drag. Turbulent flow is better for blunt bodies like a sphere or a cylindrical object since pressure drag is more dominant than skin friction drag. So now we can answer our question. Which ball, the smooth ball or the dimpled ball, would travel faster and for a longer distance? As you can see in this figure, for a smooth ball, the flow separates from the surface of the ball early, creating a broader wake region and a greater drag. However, for the dimpled ball, the presence of the dimple causes the flow over the ball to become turbulent, and hence fluid elements become more energetic and resist flow separation. We can see from the figure that the flow stays attached to the surface of the ball longer, and the wake region is thinner and hence less pressure drag. The lower the drag, the less resistant to the ball motion, and hence the dimpled ball travels for a longer distance than the smooth ball. For the same reason, vortex generators are added to plane's wing to trip the boundary layer and to make it turbulent. This delays the flow separation and prevents stalls. I hope you have enjoyed this short video and thanks for watching.